Hello, everybody. So we have been talking about differential equations, but we really haven't gotten into too many details yet about how to actually solve them. We saw a couple in the last video in their very basic form that we might be able to solve. So that's what we want to do now, is look at some methods for solving them. And the big method we're going to use in this, and probably at least one or two more videos, is something called separable equations. So let's start with a definition, and then we're just going to do two, maybe three examples. We'll see how long things take. So a separable equation is a differential equation in the form, or that can be written in the form dy dx is equal to, just want to use my same notation, g of x times f of y, okay? So what I'm saying by this, and we'll do some examples to clarify, I'm going to show us how we would solve this, but we're just saying that the x and y parts can be separated so that it's an x function times a y function, right? That's not always possible, but when it is, we have a separable equation, and the way we will solve this, we'll manipulate these symbols. We could write this is equivalent to saying 1 over f of y dy is equal to g of x dx, and then integrate both sides, okay? This takes a little justification that I'm going to ignore completely. It can be justified by the chain rule, right? So you can look at this equation that I've written right here and differentiate with respect to x and come up with what's written on the first line. But I'm gonna leave that alone. I want to focus on how we deal with these things, right? So you take integrals of both sides. Notice that on the left, I'm taking the integral with respect to y, and on the right, it's with respect to x. And then once we've taken the integral, we solve for y. And I'll say if possible. It's not always possible, and sometimes we end up with an implicit function. All right. Let's do an equation to help this make some sense. So let's try a fairly straightforward one. dy dx is equal to x over y. Okay? So this can be written in this form, right? So I'm going to rewrite this as dy over dx is equal to 1 over y times x, right? That's the same thing. You don't need to write this step out, but I just wanted to make a point. This is my function of y, this is my function of x, and they are being multiplied together, right? So we're in this form. So what I do, I'm going to take all the y stuff to one side, so this becomes y dy is equal to x dx, right? So I just took the y to this side, the dx to this side, and then I'm going to integrate, okay? Now, we are taking an integral with respect to y over here, so I get 1/2 y squared. Here I get 1/2 x squared. They both have constants of integration. I only ever write one because, you know, if it turned out that the constant on the left was 7 and the constant on the right was 15, you could just combine them to get an 8 on the right. So you could always just take them to one side. So I'm just writing one constant of integration, right? So another way of just saying these two sides are separated by some unknown constant. All right, now we're at this step where we solve for y if possible. So I can multiply both sides by 2. 2 cancels the 1/2 there. Now, it seems like I should be writing this, but again, we can be a little flexible with these constants of integration. It's some number. Twice some number is still just some number. So if it makes you feel better, we can write this as a new constant of integration. Maybe I'll write it as k. It's still just some number. The fact of multiplying by 2 doesn't change the idea that it's just some number whose value we don't know. Now, we'll finish this. I just want to point out there are times when you can't be this casual. If you have more than one constant of integration or unknown constant floating around, you might not know what they are, but they might be related to each other somehow. For instance, you can have a constant and then another constant that you know is twice the first one, or is always the square root of that one, or something more complicated. And so you don't want to lose that information. So sometimes we have to keep some of this stuff, and you have to think that through when you get there. We won't see a ton of that right now, so I'm not making a big fuss over it. All right, finally, we'll take our square root. Now, in this case, I need to write plus or minus k. I don't know the value of y, if it's a positive or negative function. And according to this, our solution, it could be either, right? And this falls right in line with, this is the general solution, not a particular solution. If we were given a particular, solution, then we would know whether it needs to be positive or negative. For instance, let's just do that. Let's say this is the general equation, but let's say I was given some extra information. For instance, y of 0 equals -3. Well, then I notice that y of 0 is equal to plus or minus 0 squared plus k. Y of 0 is equal to plus or minus the square root of k, which we now know is equal to -3. Well, now it's obvious what this must be, that I have to have the negative square root. That's the only way I'm going to get a negative out there. And then it's also clear that k is going to be equal to 9, right? Solving this equation, we get k is equal to 9. And so in this case, when we have this extra information, we can give a particular solution. Oops, I forgot the negative right after I said we need it. Our particular solution is this, right? So again, this represents a family of functions. These look kind of like absolute value functions, but a little bit off because of that plus k. And there's a family of them, and we picked out the one that satisfied our particular solution. Okay. Let's make things more complicated. Let's try a little bit more difficult of an equation. So, all right, this time we're looking at dy dx is equal to x squared plus 1 times y. Okay. Again, it's pretty obvious here that there's two functions that are multiplied together. One is a function of x, one is a function of y. So we're just going to follow the program. I'll divide y to this side, so I'll get 1 over y dy, take the dx to the other side. And then I'm going to integrate. The antiderivative of 1 over y is the natural log of the absolute value of y. And over here, I have a straightforward integral 1/3 x cubed plus x plus some constant. Okay. So using the definition of the natural log, what this means is the absolute value of y has to be equal to e to the x cubed over 3 plus x plus c. All right, so I'm going to manipulate this constant, or this expression over here a little bit. So I'm going to do some work off to the side. E to the x cubed over 3 plus x plus c is equal to e to the x cubed over 3 plus x e to the c. This is just rules of exponents. E to the c is e to the x cubed over 3 plus x. So I just moved it around. Notice e to the c, this is just e to some number, right? This is just e to some number, which can be almost anything. I'm going to just rewrite this as an a. But we should note that a has to be positive because it's an exponential raised to some number. So I can rewrite this now. I've got the absolute value of y is equal to a e to the x cubed over 3 plus x. okay? Now, let's get rid of the absolute value. How can I do that? Well, really, really simply. We've got this arbitrary constant that we gave the restriction a is greater than 0. Let's just take that restriction away. Because when we lose the absolute value, we're now saying it could be plus or minus this. And so I'm just going to keep the same. I'm just going to keep the same letter and just remove that restriction, and that absorbs the absolute value. We don't know if a is positive or negative anymore. We have to be a little careful because we now also allowed for the possibility of 0, but notice if this is if a is 0, this is just the function y equals 0. Oh, there it is, which is clearly a solution to this differential equation. If y is 0, dy dx just equals 0, and that's certainly true, right? The derivative of the 0 function is 0, and so it's kind of a simple solution to that problem. And so in that way, we get, this is our solution. There are no restrictions on a. Y is this particular exponential function. This is all in the exponent, just to be clear. And I'm going to leave it alone, but you are encouraged to try taking this derivative, putting it back into this function, putting it back into this differential equation and seeing, is the derivative equal to the function itself times x squared plus 1? I think you'll see pretty quickly that it is. Okay, I have one more example. Let's do it in another video. It's a longer one, and that would make this video excessively long. I know I do that all the time, but I'm going to try to stop doing that so often. Okay, there'll be another example coming soon. Thanks, everybody. See you in the next one.